video, which is a recording of one of my tutoring sessions with Mann. In this video and in this series of videos, we'll be discussing the deeper aspects of electromagnetic theory. What we're going to be doing is going through the chapter headings of Griffith's E&M. So if you're familiar with that text, you can kind of follow along with the chapter headings. And what I'll be doing is explaining the deeper meaning of these phenomena. I'll be explaining the experimental evidence that could have allowed people to understand this. So a bit of reduction, reducing these abstractions back to the observations which allowed us to prove them. I'll be talking about and that will enable us to get a deeper sense of what it means. A lot of times we know the equations, but we don't really know physically the entities involved and the cause and effect relationships that those equations describe. And finally, I'll be discussing some of my hypotheses of how each of these phenomena relate to the ether. And so all of that is coming up in these videos. And in this particular video, we'll be talking about the permittivity of free space, Gauss's law, Coulomb's law, and a lot of things related to the ether that relate to these topics. So I hope you enjoy this recording of my tutoring session with Mann. So electrostatics. So first of all, what we found is that a charged particle produces an electric field in line with this. Actually, let's write this out. Q over 4 pi epsilon naught E r to the fourth. Okay, this is all stuff I'm sure you're very aware of already. So the let's see. How do we know this is true? How do we know this equation's true?
I believe from empirical experimentation, right? Like we can.
Yeah, well, let me tell you, this part is from empirical experimentation. This part isn't. Okay? This part is from theory. Well, of course it's from experimentation on some level, but more directly, this part is from theory. So specifically, Charles de Coulomb used a torsion balance. So let's see. What he did is he had this stick with two charged balls, and basically when the stick rotated, it would twist this wire. Okay, are you familiar with this device I'm describing right now?
Yes, I've read about this experiment. Yes, go on.
Okay, cool. So he found that the amount of twist he could measure the force by measuring directly the total twist in the wire, and he basically found that the force diminished as the square of the distance. Okay. Now, what do you think this part is from? So this is from empirical evidence. What is this part from?
Okay. Where have I seen that? Well, epsilon I know to be the permittivity of free space, right? And
right, where did that come from? Like, what is that?
I think it's somewhat like how much charge can flow in a vacuum, but charges don't flow in a vacuum. I forget what it properly was. I did remember it. I do remember, it's in the back of my head what it is. It's not coming out.
Okay, so they actually told it's how much charge can flow in a vacuum. Yeah, it's something more like how much the electric field propagates through a vacuum. Let's actually ask. So I have my own. So you were actually told what it means. That's interesting. You were actually told what it means.
Hmm.
I was never told what it means. Let's use Chat GPT to find the mainstream answer, which is probably what you were told. What does the permittivity of free space mean? The permittivity of free space, it tells you how much resistance the vacuum offers to the formation of an electric field. It plays a key role in Coulomb's law. Okay, so it's saying basically what it's noting right here is it's saying the larger this number is,
Hmm.
the less electric field is produced by a given amount of charge.
Hmm.
Yeah, and that sounds right to me. That sounds right to me. So, how strong the electric field is for a given charge in a vacuum. Yeah, okay. So, another way to put this is that this is just a constant which converts our units of coulombs into our units of Newton, of electric field.
Hmm.
All right, so it plays the role of a constant. So similarly for gravity, we have big G up here,
Hmm. And 1 M2.
and what is it? Yeah, um, and big G is all it's doing is it's telling us like how strong gravity is basically, and then it's making a unit conversion from the units of mass and distance. It's making a unit conversion from those units of mass and distance to units of newtons.
Hmm.
So that's one role that a physical constant plays.
Hmm.
Okay. Now, there's more. Like I'll tell you a little bit more to the story later, but that's all for now. Where does this come from?
Hmm. We can 1/4 pi has no units, and so we are finding an electric field, right? As you said,
Mm-hmm.
it can be found by just you know like the units of it can be found by just like like putting everything else that needs to cancel out other than the charge and the square of the radius into one constant. So that can give a hint towards what it is that we're trying to find, because what we're trying to find is a proportionality constant of some sort. you know like we know that the
Mm-hmm.
electric field is directly proportional to the charge and inversely proportional to the square distance, like the square distance law. And then now, for that proportionality to be converted into an equality, there has to be some k here that relates everything. And then we just uh, put the k on one side of the equation, send everything else on the other side, and then we have the k, you know, something like that.
Um. So it sounds like you're explaining K. You're not explaining the 4 pi though.
Yeah, I don't know what how the 4 pi came around.
So
Well,
here's where the 4 pi
see
comes
here,
from.
like,
The 4 pi comes from a theoretical stipulation basically. And this theoretical stipulation ends up getting proven, but for now I'm just going to propose it to you as a hypothesis. The electric field might, a charged particle might shoot emanations in every direction.
hmm,
Okay, it might be like a charged particle. The electric field might be these emanations that are shooting in every direction, and if that's the case, then they're spreading out spherically.
hmm,
They're spreading out spherically. So as a result, the electric field might be the emanation density as it hits a certain location. Here I drew a little dude that is getting hit by the emanations. So it's like the density of emanations that he's hit by the density of emanations that he's getting hit by it might simply be proportional to the total emanations. So let's call that I, okay, divided by the area over which those emanations are spreading. And what is this? This is the area of a sphere.
Yep.
So this whole thing, except for E, don't worry about E for a second. This whole thing, except for E, I mean, this whole thing, it comes from a theoretical stipulation that the charge is shooting some kind of influence out in every direction, and that it's shooting some kind of influence out in every direction, and that influence is spherically spreading. Okay.
Yeah.
Okay. Now. Okay. So. That is the stipulation. Any questions on that?
No, it seems quite straightforward. Like, it makes sense. Like,
Yeah.
it makes sense.
Okay. So let me. I'll say one more thing. In experiments that came way later, you've probably heard me say this in one of my YouTube videos, but in experiments that came way later, we see that if there's a change in the position of a charge, it takes the speed of light for the electric field to change at a given location.
Yes.
So as a result, we've actually, that experiment, I mean, really that experiment is a measurement of the speed of light. Like, once you understand that light is an electromagnetic wave, you've covered that in your class, right? That light is an electromagnetic wave, and like okay, so once you find that light is an electromagnetic wave, that proves that these emanations are shooting out at the speed of light. Okay, how does it do that? Let me show that real quick. Basically, what is light? Light is caused by the up and down, by the oscillatory motion of a charge. And so what does that do? That's changing the electric field in a way that propagates over to some receiver. Okay, so that shows that the electric field, you can think of it as at all at least it's as though the electric field is constantly propagating out at the speed of light. And so if something changes about the source, then the electric field will change in a spherically spreading way. Okay. Now what's interesting is that the magnetic field changes also.
Okay.
But that's a whole nother story. For now, we're just worried about the electric field. So I'll tell you that basically we know that these changes propagate outward at the speed of light at some finite speed. We also know that they obey an inverse square law. So as a result, here's the argument.
Okay. Yes. We're back. Okay.
Did you lose me?
Yeah, just for a minute. Not even a minute, like 20 seconds.
Okay. I'll repeat the argument then. So the emanations travel at a finite speed. We've proven that from experiments. The emanations decrease in power as the square of the distance. Okay. As a result, we make the following argument. We say this field has all of the properties of spherically spreading emanations. Therefore, they are spherical spreading emanations. Okay? So you can see we can't actually see the emanations spreading out spherically, but it has all of the properties of spherically spreading emanations. So as a result, we've proven that they are spherically spreading emanations. That's the argument there, okay? Now, this argument leads to Gauss's law. This argument leads to Gauss's law. You studied Gauss's law, right?
Yes.
Okay, let's go over that now. So, if we keep up at this pace, this will be great because you'll basically understand
Mm. And
like all of my insights for this class in a pretty short number of sessions. So
yeah,
that's
and this is
that's
how
pretty
I
nice.
used to imagine electric field and flux usually, you know, like uh, like this. So far, it lines up with my intuition a lot.
Right.
Mhm.
It is very intuitive, but of course, more importantly, I've connected the dots. I've shown how the evidence leads to the conclusion.
Right.
I've done a very quick, sloppy induction, basically,
Mm.
is what I've done here. I've connected the dots and given the arguments that allow the uh, and allow it to connect. Okay, allow us to connect the observations to this intuitive conclusion. So
Mhm.
let me write out Gauss's law. Yeah. All right. And you're familiar with it being written like this?
Yes.
Okay, so this is Gauss's law. This is Gauss's law. And the let's see. What is Gauss's law saying?
The electric field of a given enclosed area is directly proportional to the charge and like equal to the charge divided like enclosed charge of that area. Like
Well,
not area, but you know.
this is specifically talking about the flux.
Yes. Yeah, the
It's
flux. Yes,
not
yes,
just the
yes.
electric field.
The flow of
And
electric.
what is, yeah, the flux, the flow. Yeah,
Yes.
good. Now, so, okay, what I want you to explain to me is, so here's the electric field lines in here,
Mhm.
and then out here are like flow lines. It's telling us how much is flowing through.
Mhm.
Okay. Now, so what this integral does is it integrates over every single little piece of area, right, of our arbitrary shape. It integrates over every little piece of area.
Mhm.
And, okay, here's some weird stuff. I want you to explain this to me. A is written as a vector. You see
Mhm.
that?
Yeah.
And then we're dot producting it with the electric field.
Mm.
What the heck does that mean?
Well, area can be a vector, right? Depending upon if, especially if we're talking about flow. So, area like okay, like if something is coming out of a sheet or something is going into a sheet, you know, those are two different directions to the same area, I guess. And if we go into the
Uh-huh.
more linear algebra side of things, uh, like there can be, you know, like uh, what can we say? Like a vector, let's say two-dimensional vector space, and then add uh, any anything in the third dimension, then that kind of stimulates what we're talking about here, I guess. Like I'm trying to like connect the dots, but like when we create a three-dimensional vector space, we have to add one more vector to a two-dimensional vector space, which is correspondingly area. Like it is like a sheet of like a sheet of paper, like something like that, you know.
I'm not following that. You might be talking about a certain kind of advanced way of thinking about this.
Hmm.
I'll just give you my basic way of thinking about this. I
Hmm.
like to think of the area vector. The area vector is a vector that points perpendicular to the surface of that area.
Mm-hmm.
And so what does that do? What that does is it tells us the direction that the surface is facing.
Yep, yep,
Okay.
yep.
So that's okay. And then it has a length that's equal to the area.
Hmm.
Okay. Now, why on earth would we think about that? And why are we dot producting it right here? What's up with this dot product?
Hmm. Well, we want the entire flow to be represented as one number. And through every piece of area dA, there is a certain amount of electric field flow, which corresponds to as EDA, you know. And if we want all of it, then we want it all in one number. And if we can assume that both of them as vectors, storing relative data of the electric field and the area, then we dot product them to get it in one number, I guess.
Good. It sounds like you understand this really well. Let me ask you, though, how well do you feel like you understand this?
I feel I'm a little rusty, but I have the intuition. Like I
You know,
studied
so
quite well
don't,
for these.
we don't we don't want intuition. We want knowledge of what's physically happening. That's what we want. And
True.
now, once you have that knowledge, it might feel intuitive, and that's good. I'm glad it feels intuitive for you. But really, like, nature doesn't care about our intuitions. Nature
True.
just is the way that it is. Like, I think the reason the word intuition gets thrown around is because of the following attitude that physicists have. The attitude is, you're never going to understand the cause and effect relationships going on here.
Mm-hmm.
Nature's absurd. It's complicated. You're just never going to understand it. The best you can do is to form this picture that conforms to your human biases and feelings. Now, that picture has nothing to do with reality, but at least it helps you remember how to solve the problems. That's the perspective that this word intuition, you've probably heard the word get used a lot by your professors or on YouTube channels, and not everyone using that word means it with that like full corrupted context. Like, dialect on YouTube. You've seen dialect videos, right?
Yes.
Yeah. Really good physics videos. He uses the word intuition at times. Like, he obviously doesn't mean it in that fully corrupted sense,
Mm-hmm.
but but that's its origin. And to the degree we use the mainstream concepts that are corrupted, we are participating in that corrupted kind of thinking to a certain degree, not to the same degree they are, of course. But the way to fully break free from the mainstream is to use the terminology differently. Just as objectivists need to stop using the word selfish in the way that other people use that word, we need to start using words like intuition, locality. A lot of different words need to just be. We need to use them differently.
Yeah.
Is how that's going to work.
You know,
Yeah.
what you
So
described to me just now, like that's the mentality of someone uh, who has to complete an 8-hour assignment in 4 hours. Like, it'll get done somehow. I'll not understand it, but it needs to get done. You know, but that doesn't
yeah.
lead to actual knowledge. That just leads to, you know, subpar, approximate maybes. You know, it
Yeah.
doesn't lead to
And the
perfect
reason
physics.
Yeah. The reason you're being given that much work is because your professors, I mean, if your professors in India are anything like they are in America, which they probably are, but I don't know. But if it's anything like it is in America, then your professors, they think that being able to do the problems is really the only sign of understanding it. Because trying to like probe the student in the way that I do by asking questions, probing the student for their actual understanding of the experiments and how that leads to an understanding of the actual cause and effect relationships that man can infer from those experiments, that's just way too hard. I mean, at least, I mean, I don't know if it's too hard, but basically, the way I do it is by asking the student questions, and it is hard to figure that out. And in general, the education system has not come up with some kind of way to test for actual understanding. And as a result, like, and then further, because they have this corrupted view of what it means to understand this stuff, they don't think you can actually understand the observations and inferences that allow us to know that these fields actually exist with certainty. Because they don't believe in all of that, they don't recognize a difference between bullshitting your way through it and like getting the right answer over and over again, and truly understanding the reasoning that led from the observation to the the understanding of fields that we have today. And for my own part, when I was in college, I spent almost all my time trying to decipher the physical meaning of this, and there was very little time left over for the math. And I thought, and I stuck true to the idea that the way to understand the math was to understand that physical meaning. But I was on my own. I had to do it all myself. So part of our purpose today is to convey, or I mean, I don't know, over the course of our sessions is going to be to convey all of my knowledge that I've accumulated in understanding the true physical meaning of this stuff, convey that knowledge to you quickly.
Mm-hmm.
That is that's our purpose.
Mm.
So that's really good. It sounds like you understand this really well.
Yeah.
So each little bit of this surface right here is turned into a little, you know, infinitesimal area element that we're calling dA, and it has, this dA vector, and by doing the dot product, that finds the flow through that little area.
Mm.
Okay, I have a question though. How does a dot product find the flow through that little patch of area?
Mm. So let's think about this. Okay, what does a dot product do? It compresses a lot of vectors down to a scalar. Okay. Uh, why can't this have?
It condenses two vectors into a scalar.
Yeah. Yes.
Yeah.
So let's say, okay, it's in effect, let's say there is, I have a tank with a tap in it, and I need to find out how much the flow through the tap is. So I'll have to, in effect, multiply the amount of, I guess, the water in the tank with the area of the tap in some way to get like something along those lines to get to the flow equation, I guess.
So you're saying this is like a tank,
Yeah.
and there's some water in there.
Mm-hmm.
Okay, and then what?
And then, uh, okay, this would not work properly, but let's assume, let's take there is a small hole in the tank, and we want to find out the flow from there. So we'll need the area of the hole, and we'll need the, let's say, volume of the water inside. Uh,
Okay.
right? Because the water has to go through that area to go outside, and we need to know how much
Mm-hmm.
water there is, so that like how much
Mm-hmm.
of it has to go outside, and like at what rate of flow. So those would be the two
Okay.
variables needed, and uh, like volume can be represented as, if area can be represented as a vector, uh, like the amount of water can be represented as a vector. That can be the electric field example, I guess.
Yep. Yes. Yes.
And to find out the proper flow, you need both of these. You need the volume going, the amount of stuff going through a particular area, and you need one
Uh-huh.
number.
Uh-huh.
So what gives one number for two vectors? Dot product.
One number for two vectors. So you're saying that we have like a flow vector of the like it's the flow of the water.
Mm-hmm.
Maybe it's like velocity. Let's see. It's going to be velocity times mass.
Mm-hmm.
And so it's going to give a certain number of kilograms per second, kilograms times meters per second, and it's going in a certain direction.
Mm-hmm.
Actually, it's not going to be. It's going to be. We're actually the proper way to do this, just so you know, is going to be velocity times density. Velocity times the density of the water, and you'll see why those
Yeah,
are the right units in a moment.
I do
Velocity seen as
remember
a vector.
I do remember like fluid dynamics a little bit. So I was like, I was trying to relate flow between this and that in some way. Like there is a connection. I know, but
Yes, yes, there is. There
Mhm.
is. You're totally on the right track. And I'm drawing this. So these are like particular locations where the flow is punching through the surface, is what I've drawn here.
Yeah.
Um, and you're totally on the right track. In addition, Maxwell modeled he modeled electrostatics as being fluid flow.
Mm.
Um, so he modeled electrostatics as being fluid flow. So you're totally on the right track here. And you've said that a dot product is a way of taking two vectors, these two vectors,
Hmm.
and then getting a scalar. And we want a scalar because the flux is a scalar. That's what you've said, right?
Hmm.
Okay.
Like we want a
This
number which
is
describes the entire phenomena, with
yeah. And we
phenomena in the
know the
Kantian sense.
phenomena.
Like, uh, you know, like we need a
Okay,
number
say
which
that again.
describes the entire thing, without focusing on the particulars of this particular area or that particular area. We want, well, how much flow is there in total, you know?
How much flow is there in total? Yeah. Okay. Yeah. Without worrying about the velocities or areas that gave rise to that.
Hmm.
So again, you're saying like we're looking for a number, a specific number. So all of this is right, but we're missing something here.
Hmm.
We need a full, thorough justification for why a dot product is appropriate. The justification you gave is insufficient. The
Hmm.
justification you gave is it comes out to a scalar. Well, yeah, a scalar certainly matches the kind of thing we're looking for, namely flux, but it isn't sufficient to say, well, like, why specifically is a dot product? We need to connect the physical cause and effect relationship to the use of the dot product here. And that's, and I'm saying this because I'm really trying to teach you the right mindset for finding the physical meaning of these equations so that you can start finding physical meaning for equations in the future.
Hmm.
So how do we know a dot product is appropriate?
Okay, so properly, what a dot product? Okay, what's the definition of a dot product? Let's go there.
Yeah,
You know, so
yeah.
hmm, I'll have to look it up. You know, I don't have it on the top of my
Let
mind.
me go ahead and tell you, I actually explained this in my video on the dot product and cross product. Let's
Hmm.
say we have the vector A dotted with the vector B.
Hmm.
What does the dot product do?
Hmm.
What does it do?
It,
So we think of
it
B
projects.
and we think of,
You know.
yes, it does. Yes, part of what it's doing is it's projecting. and not in the Freudian sense, but in the geometric sense.
Yes.
Um, so, okay, so what does it do? What we do is we project B onto A. Now you'll notice that I didn't write this as a vector because what we do is we simply write this as a scalar. This projection is written as a scalar, so it's B times the cosine of theta. And notice I didn't put a bar here because that's my way of writing a scalar, is to not write a bar. A lot of people do this. They'll like put why do that? Why do extra hand exercise? Because it's just if there's no bar, then it's a scalar. If there is a bar, then it's a vector. Okay, so
Also,
that's the
isn't that
way.
used for
Of course,
like norms?
actually,
The
what's that?
double, like the lines around the vector, isn't that used for like the norm of the vector space? So wouldn't that lead to confusion?
The norm of the vector space.
And it's quite
Um,
irrelevant. I was just adding to your point that that's a bad way to do it.
well, I think there actually is a decent reason to do this now that I'm thinking about it, because if you just write A, then that just implies that A is a scalar. But if you go like this, it says A is a vector, but we're taking its magnitude. So I think there is actually a point in doing that.
Mm-hmm.
So I will continue. So we've questioned the mainstream, and now we've found, I think, in my opinion, I found that the mainstream is correct on this. So I'm going to go ahead and do what they do. All right. The dot product is then equal to the magnitude of A times the magnitude of B times the cosine. Okay, now what's the point of this? What's the point of this? It takes the part of the B vector that lies along A, and then it multiplies it by the magnitude of A. And that's what this is. That's what this is. Okay, now that I've described this mathematically, there should be a question of like, well, what the hell is the point of this? Well, in order to understand the point of this whole thing, I want you to tell me why a dot product gives us the flux in this situation.
Well, we want the flow of the electric field along the particular area, right? So we want it projected on the area.
Yeah, the area vector.
Yes.
In other words, we want the component of the flow. This is actually a little annoying with these fatty arrows. We want the component of the flow. So here are these flow lines. So these are the flow lines. Well, I mean, they're the electric field lines. Here are the electric field lines. Let's try to write this better than a kindergartner would. Then this is what we can call E perpendicular. It's the amount of E that's actually punching through the surface. See, at this location, there's two components. There's an E parallel, which does not flow through the surface, and there's an E perpendicular that does flow through the surface. And by doing the dot product between the electric field vector and the area vector, you're only finding the amount that punches through the surface, and you're multiplying that by the small amount of area.
Yep.
Okay? Now, so to finish up on the dot product, notice that the reason we even constructed this mathematical abstraction to begin with is because there are a lot of situations where we're interested in taking just the part of one vector that goes along the direction of another vector and then multiplying those parts. Okay, so and the example I use in my dot product and cross product video is work, and is work basically. So and that's just simply another example where you want to do this mathematical operation for particular reasons. So Okay, now let's complete our thinking regarding the fluid flow. We think of the fluid flow as the what's it called? The velocity vector multiplied by density. But now, but well, that's not the fluid flow. That's the equivalent of the electric field. The electric field is like a velocity times density. But then we multiply that by an area. And let's think about what that's doing. Let's think about what that means up here. We have a certain area A, and it's going at a certain velocity. Well, if you multiply the area by the velocity, what do you get? You get
The volume.
You get a volume per second. If you then multiply that volume per second by the density, which I did here, then you get a mass per second. And so the flux is like mass per second if the ether is indeed a fluid flowing around, and the flow of that fluid is the electric field. Now, the ether probably isn't like that. We're going to learn stuff later that shows us that the ether probably is not like that. But but this is the first hypothesis that Maxwell brought to this problem, and it was a very reasonable hypothesis in this delimited context of knowledge. Yeah. Okay. So that's some stuff about Gauss's law. I'm going to give you one more interpretation. So, okay, now we're going to keep thinking about Gauss's law. You understand this side of the integral now. You understand this side of the integral. Now I have a question. How do we know this equation is true? Copy. Let's go. Let's just rewrite it. Let's move away from all of that and start with a fresh sheet here. How do we know this equation's true?
Well, we have to. Two ways can be to either have some way to test it empirically, or like have a proof of it from first principles which were tested empirically. So what can we do here? Can we can study the effect, a particular physical effect that such a flow can have on a given unit area. Maybe a very thin metal sheet which is susceptible to interaction with electric fields. Probably do something like that,
We could test it, and we could see that the equation got the right results for certain experiments. Although measuring flux, I'm not 100% sure how you would do that, but there's a problem with, even if you could, there's a problem with testing it. There's two problems. Number one, if the equation gets the right answer over and over again, that raises the chances that it's going to get the right answer next time. So that's kind of nice. But here's the problem. Two things happen. It doesn't tell you the physical meaning of the equation, number one. And it doesn't tell you if the physical hypothesis that lies behind that physical equation, it doesn't tell you whether that physical hypothesis is right or not. It just tells you the equation gets the right answer a lot, and so it's likely to get the right answer again in the future. But it doesn't offer you any physical insights. Number two, there's a question of, well, how the devil did they even get this equation? Like, where did this equation come from? Did Maxwell, it's really Gauss's law? Or wait, what do they call it? Yeah, they call it Gauss's law in this class. Did Gauss just smoke a bunch of weed one day and then, this popped into his head? Of course not. This was based on some physical hypothesis of what he thought was actually going on in the case of a electric field or a gravitational field. I find it more likely Gauss was thinking about gravitational fields, but everything is the same regarding that. So this is part of the inductive process of reverse engineering all of these equations. Modern philosophy has stripped these equations of their physical meaning, and we're either given no physical explanation, or we're given a physical explanation and told that it's an intuition, like, oh, well, this is a way to make your puny human brain understand it, but really it's just pure math floating around, and there's no way to understand it until you reach Plato's world of the forms, and then blah 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 blah. But only the really smart people can do that. So that's the attitude that's more or less implicit in a lot of the way this is taught. But let's actually get to its physical meaning.
Yeah.
To get to its physical meaning, we're simply going to make deductions from the statement that we've proven that charges shoot some kind of emanation in every direction, and that those emanations travel at the speed of light, and that they're constantly shooting these emanations. We're going to talk a little bit at the end about shooting. Shooting is a little bit of a problematic word, but for now, let's just think of it that way. So, shooting's a problematic word because some people are offended by guns. No, that's not why. It's problematic because it may not be physically true. So anyway, but for now we'll just think about it shooting. We can make deductions from the hypothesis that it's shooting in every direction. Okay, here are the deductions. You have some kind of area of some arbitrary shape, okay? And you have a couple of charges in here, and they shoot their emanations in every direction, okay? As long as the surface is, and this is shooting emanations also, here we go.
Yep.
As long as the surface is completely enclosed, then every single emanation gets counted by the surface. The surface receives flux from every single emanation. There's no holes in this surface, so there's no emanations that are going to shoot out of the surface without being counted as flux first, right? So the amount of emanations that flow through the surface is equal to the number of charges inside the surface divided by a particular constant.
Okay.
So you can see Gauss's law is glorified common sense once you understand the idea of emanations. It's mathematized common sense is what I should say. Mathematized common sense. To make this a little easier to understand, and just because I like this example, imagine that every charge is a hand grenade that's exploding and throwing fragments in every direction. The way to think about this is you have a room. You open a door. The room has only one door. You open the door, you throw hand grenades into the room, then close the door. What is Gauss's law saying? It's saying the number of fragments that hit the walls is equal to, or is proportional to, the number of hand grenades thrown. And this is a constant that tells us something about the number of fragments thrown per hand grenade. Okay, any questions on that before I move on to explaining epsilon naught in greater detail?
So far, agreed. But how does it get us closer to the problem of, okay, we have given an explanation of why this equation works. All right, makes sense. Okay, so now we know that it works from experimentation somehow. Like, not somehow, but like there is experimentation. And we know why it works.
Yeah, that's a good. Yeah, well, so what we've gone over so far is not the experimental confirmation.
Mm-hmm.
Rather, what this is from the earlier argument I gave. What's the earlier argument? The earlier argument
Mm-hmm.
is, hey, these forces obey an inverse square law, and these electric forces, they obey an inverse square law. And we know that the emanations travel at some finite speed. Therefore, we know that there are spherically spreading emanations. Why? Because this situation has all of the properties of a spherically spreading emanation.
Mm.
Okay, now we're going to talk about what I mean by an emanation in a moment. For now, it just means a phenomena which propagates outward spherically. That's what I mean by emanation. Um, so, let's see. Given the fact that it's a spherically spreading emanation, it will obey this law.
Yeah, because any spherically spreading emanation would obey that law.
Yeah.
Mm. Yeah.
Now, it's important to note that I haven't given the experimental justification for this.
Mm-hmm.
Why do we need, but there's a question here. We've already confirmed that it's an emanation. All we've done now is we've deduced from knowledge that it's an emanation into this further knowledge.
Mm.
What would be the point of an experimental confirmation? Well, I don't think confirmation is quite the right word, but experimentally testing the equation is a good idea. But it's not to check whether the deduction was done right. We know that the deduction was done right. Now, you may have messed up the deduction somehow, so
Mm.
maybe you check it. But really, the reason for a further experiment to test the equation is not because you're afraid it's not an emanation. You already know it is. It's not because it's because you're afraid that this math somehow doesn't work out. As long as it is an emanation, the math will work out. So what's the point of testing it?
Mm-hmm.
The point of testing it is to see if there are additional factors at play.
Yeah.
If this equation doesn't end up being experimentally correct, it doesn't disprove your earlier knowledge. You know the electric field is an emanation. We've already proven it.
Mm.
We know that an emanation will behave this way. What it means is that there are additional factors at play which prevent this equation from being exactly true. So the purpose of a test like this is to explore to explore for additional conditions upon the law. This is an area of this is what my theory of induction calls an unexplored territory. You know that you could test this, but you haven't yet. And you know that if you were to test it, you might find additional phenomena, which is always in our interest to look for.
Mm-hmm.
So I prefer to think of it not as a negative motivation, like, oh, we need to make sure we're right. It's a positive motivation. We're looking for more facts. And this is a way to find them. Because if there are more facts, then this equation won't hold. If there are not, then the equation will. And now we know that there's nothing under that rock. We've turned over the rock, there's nothing under it. So look under other rocks for more phenomena. So that's how I like to think of the scientific method as it applies to these kinds of theoretical discoveries. These discoveries that were made through deductions from the known phenomena. Okay, now one final statement here. I'm going to take this law and I'm going to take this part, the 1 over epsilon naught, and I'm going to change it into a constant. And since I'm lazy, I'm just going to call it K. All right? If we write if we write it this way, copy, then Gauss's law it starts looking like this. It starts looking like this. Now, what does K mean? K means, here's what it means. It means the number of emanations per Coulomb. Can you see that from the equation?
Yes.
Yeah, because this is the total number of emanations. These are the number of coulombs. And so this is just a constant that tells us how many emanations, like how many fragments does the grenade throw out, basically. And this is emanations per Coulomb, or more specifically, like electric field produced per Coulomb. Okay, so that's one way to think about the physical meaning of this. I think the way Maxwell thought of this was probably a little bit better, because he was thinking, he thought about this, and he thought about this as like the resistance that the ether gives to like the Q changing the ether in its vicinity. In order to explore that, I'm going to make my last point of the day. Let's see. What was my last point? Yes. I'm going to tell you about the problematic idea of shooting. So there's one hypothesis is that the charge is shooting something out in every direction, just like a hand grenade. There's a problem with this. If this is true, it means the charge is shooting constantly. It's like a hand grenade that's constantly exploding and constantly throwing out fragments.
Yeah.
If this is the case, then yeah, exactly. Apparently the charge has unlimited ammo. So I find it unlikely that that's what's going on. Because we've never seen any examples of a charge actually depleting its ability to influence the ether around it. So I think what's more likely is not that there is a, what do I call this? Dang it. There's two, it's not, I forget what my name for this is. This is part of my theory of induction. I forget what my name for this is, but like basically it's not shooting an entity in every direction. Rather, it is an entity, and there's an entity around it. There's an entity around it, the ether. And the entity is influencing, is causing some kind of influence upon the ether. And that when the entity changes its position, the way it influences the entity will change, and that change will propagate outward at the speed of light. So one toy hypothesis for how that works is that, and this was Maxwell, I shouldn't call it a toy hypothesis because this is really similar to Maxwell's hypothesis that made a lot of good progress. Maxwell thought of it as a pressure. He thought of it as that the positive charge is producing a pressure gradient in its vicinity in the ether. So this avoids the issues involved with shooting. It means that the charge doesn't have unlimited ammo. There's a way to think of this. So what that means, by the way, is, and we're going to get to this later when we start talking about voltage or electric potential. I have a feeling that like voltage, electric potential, that is closer to the actual meaning. It's just a feeling. It's closer to the actual meaning of the field, the actual physical cause of the field. Because voltage is more like a pressure. Voltage, Maxwell thought of voltage as a pressure, basically. That's all I'm going to say about that for now. Okay, and how does that, so if that's the case, then this is like, it's telling us how strongly the charge can affect the pressure nearby. And of course, we know that dielectric materials can make this number larger or smaller to make the electric field stronger or weaker in a given at a given location, basically. Yeah, and I believe it makes it smaller. Let me look into that real quick. Because like it makes it so that the electric field gets stronger inside. Let's see. Dielectric constant equation. So let's see. So K is or kappa is the dielectric constant. You've seen this, right?
Mm-hmm.
And it's equal to the permittivity divided by the permittivity of empty ether. Now, yeah, you'll notice I don't like to call it permittivity of free space because that makes it sound like it's like a vacuum. In fact, a lot of times this is called the vacuum permittivity, but it's not a vacuum.
Which is one of the questions that first comes to mind. Like if like permittivity of a vacuum. Okay, well, a vacuum should be infinitely permittive, right? Like there's nothing there. Like who's giving the permission?
Well, yeah. I mean, I prefer. I don't know if that's right because I think if you really mean a vacuum where there's nothing there, then you're already lost. You're already wrong because there is no such thing as a vacuum because nothing isn't a thing. Nothing is not some positive existent. That's what I call Parmenides' principle. That's also featured in my theory of induction. So, okay, so anyway, yeah, it's the permittivity of empty ether. Let's rearrange this son of a gun. Kappa is times the permittivity. So this is interesting. Apparently, the dielectric constant makes the permittivity larger. It would appear. It would appear that it makes the permittivity larger. Let me see. Let me just ask something to confirm it because if we don't get the right answer, does the dielectric in a capacitor make the permittivity smaller? Let's see. No, the dielectric increases the permittivity. Which I am a little bit concerned with because if it increases the permittivity, that means it's decreasing the electric field inside the capacitor, which confuses me a little bit. But we'll have to leave that mystery for now. We can definitely see that the permittivity offers like a resistance to the way that a charge changes its field. And so it changes the field around it, changes the ether around it. And you'd think that a smaller permittivity would then make a capacitor more effective at holding charge. But maybe I must be missing something. In order to do that, we'd have to go into the details of a capacitor, which we'll do later. That's just going to be our next section. So we'll just keep going through these headings, and you've already been introduced to these ideas once, and we're going to keep doing two things. We're going to keep connecting, or three things. We're going to connect everything to experiment. We're going to do the deductive reasoning steps from those experiments that led to these abstractions, like Gauss's law, and we're going to what was the third part? And we're going to, when possible, make hypotheses about what this tells us about the nature of the ether. That's what we'll do at each stage. And by the time we get through all of this, you'll be completely caught up in terms of my thinking on all of these issues. Any questions before we go?
No, I understood so far. And I also remember the permittivity being increased. I think I'll look it up. I have it somewhere stored. like I also had some doubts about that, but I did like a deep dive on Chat GPT, and I like restored some
Yeah,
confidence there. So I'll look that up as well. And
cool.
so far so good.
Cool. Yeah, yeah. Look that up, and we'll cover that in our video on capacitors, which is going to be in just two videos. It'll be our third video like this.
Mhm.
So
And
yeah.
I would like to like contrast this like one session with like perhaps 4 to 5 years of just working with electronics and like both theoretically and practically in high school and here, and like nobody has explained like this. you know like I can
Well,
solve
yeah,
circuits with the best of them, but
yeah. Well,
yeah.
this is good. It's good because in America we tend to not get the hands-on application.
Hmm.
We go through labs, but they're a joke. You don't learn anything in them.
Hmm.
So it sounds like you at least get this, and I mean it here. You get an intuitive sense of how circuits work. They just drill it into you a lot. They just do a lot of lab work with you, which is really good. It's irreplaceable, but
Hmm.
it's worth noting that it's really not enough to understand what's going on. You need to do extensive thinking that consists of inference from those experiences. Um,
Hmm.
the actual experiments are um, irreplaceable, and I have to say that it's kind of a weak point of mine that I haven't done many of the experiments. I've looked at them a lot, but I have focused on elucidating the physical inferences from those experiments to get to the abstractions because they're both important. Um, a focus entirely on lab is like an empiricist approach. In America, in American universities, at least the ones I've been at and taught at, it tends to be a rationalist approach where we pretty much completely focus on the theory. But you need both, of course. So,
Hmm.
yeah.
Yeah.
Cool,
And
dude. Well, I'll see you again soon.